Continuing our discussion of generalized Biot-Savart law, first we've calculated V cross R hat vector. That's what we have to calculate to get this integral. And in part E, an area element on the cylinder may be written as dA equals capital R dx d phi. Use this and the previously established information to write the generalized law of Biot-Savart as a double integral. Evaluate the integral to determine the magnetic field at the center of the cylinder and compare with 28.76 result. Okay, so first of all, y is r d phi dx, the area of this element. So if you do r d phi, you get the arc length. If you go on the x-axis by an amount dx, you get this basically small area element. Okay, so let's write generalized Biot-Savart law in part E, noting that the area element has an area, differential area, dA is equal to capital R dx d phi. So we're going to write a double integral. The generalized Biot-Savart law is mu 0 over 4 pi. Magnetic field is equal to mu 0 over 4 pi integral sigma v cross r hat over r square dA, and it's in I hat direction. Why is it in I hat direction? Using the right hand rule. So we can see that these charges are moving counterclockwise. 4 fingers of our right hand curl in the counterclockwise direction. The thumb points in I hat direction. Okay, so if I substitute the results I have found previously for the magnetic field, this integral will be mu 0 over 4 pi is a constant. The distance dx will go from minus w over 2 to plus w over 2, and the angle phi will go from 0 to 2 pi. So how do I find these limits? Well, this is the origin, so it's minus w over 2 to plus w over 2. Basically, that's where this point is and this point is. And if I vary the angle from 0 to 2 pi, then I will have accounted for all such area elements. So this will be sigma, which in part A I have found to be the total charge Q divided by 2 pi capital R W, V cross R hat over R square. So V cross R hat was RW. So I have RW and another R coming from dA. So this will be capital R square W omega divided by angular speed omega divided by R square. Now R square is x square plus capital R square multiplied with this gives me x square plus capital R square to the power 3 over 2. Then I have R I hat minus x cosine phi j hat plus sine phi k hat, and the phi integral d phi and dx. Okay, so if I rewrite this, first of all I notice that one of the r's will disappear, and from this 4 pi and 2 pi I will get an 8 pi square at the bottom. So this magnetic field B is equal to mu 0 divided by 8 pi square W, and then there is Q capital R Q capital R and omega, the angular speed, on top. Then I have the integral over x from minus w over 2 to plus w over 2 integral over phi from 0 to 2 pi. And if I write this ratio, capital R I hat minus x parentheses cosine phi j hat plus sine phi k hat divided by x squared plus capital R squared to the power 3 over 2 d phi dx. That's the integral I'm supposed to evaluate. And this is going to be mu 0 q capital R omega divided by 8 pi square w. If I do the phi integration, minus w over 2 to plus w over 2, that's x integration. The phi integration will give me a 2 pi. So 2 pi r I hat. 2 pi capital R I hat. The phi integration for this part will give me minus x. Integral of cosine is sine phi j hat. Integral of sine is minus cosine phi k hat, which will be evaluated between 0 and 2 pi. Sine and cosine are periodic with 2 pi, so these two evaluations will give me 0. So this is going to be, this part will give me 0. So I will be left with only the x integration, x part. Okay, so if I rewrite this integral here, magnetic field B is equal to mu 0 capital Q capital R square angular speed omega divided by, because I have a 2 pi r here, 2 pi and 8 pi square will give me a 4 pi at the bottom, 4 pi w in I hat direction, and this integral remains minus w over 2 to plus w over 2 dx over x squared plus capital R squared to 3 halves. That's the integral I have to evaluate. And if I do this substitution, let's draw this right triangle here. And let's call this angle theta. Tangent theta is x over r, or x is equal to r tangent theta substitution. This will give me dx is equal to capital R secant square theta d theta. So I will work with this substitution. The integral of dx divided by x squared plus r squared to 3 halves is then going to become the integral. For dx I write capital R secant square theta d theta, and at the bottom I will have capital R cube. So if you take this to capital R square parentheses, you will get capital R cube. This will be 1. This will be x squared over r squared, which is tangent square theta. 1 plus tangent square theta, I know, is secant square theta. So this will be r cube secant cube theta. Okay, so if it is secant square, the square and 1/2 will cancel. I will be left with secant cube theta. So this will be 1 over capital R squared integral of 1 over secant, which is cosine theta d theta, which is 1 over capital R squared sine theta. And what is sine theta here? The hypotenuse is square root x squared plus capital R squared. Sine theta is x divided by square root of x squared plus capital R squared. So that's the answer for this integral. So if I go back to my limits, what about the integral from minus w over 2 to plus w over 2 dx divided by x squared plus capital R squared to the power 3 halves? This will be 1 over capital R squared. I will have for x w over 2 divided by square root w squared over 4 plus r squared square root. And if I do this for both limits, and so evaluate at w over 2 minus the evaluation at minus w over 2, this will be just twice this result. So I will obtain w divided by r squared 1 over so you can see here w squared plus 4r squared over square root of 4. That will give me another 2 here. So this will be 2 over square root of w squared plus 4r squared. Okay, so this 2 multiplied by this 4 pi will give me a 2 pi at the end. So for this magnetic field, I will have P is equal to mu 0 q, going back to my integral, mu 0 capital Q r square omega divided by 4 pi w multiplied with 2w over r squared, and then I have 1 over square root w squared plus 4r squared. So this 2 will make, w's will disappear, this 2 will become, make the bottom 2 pi, and this is in I hat direction. So the final answer for the magnetic field is then mu 0 over 2 pi, mu 0 over 2 pi, because I have a cancellation of these r squares here, q omega, q angular speed omega, divided by w square plus 4r square square root in I hat direction. So that's the final answer for the magnetic field. Now our task in part F is to compare this result with that of problem 28.76. So this was 78, 77, here is 76, and that's the answer we have found for this rotating cylindrical shell. So it gives exactly the same answer, mu 0 q omega divided by 2 pi square root w squared plus 4r squared. So for F, for part F, I'm going to write this result, this answer agrees with that of problem 28.76. So that's what I have found. Okay, so in this part, that will be written for the end. Okay, so that's the answer to part F. So for this part, I have used the answers I have obtained in parts A, B, C, and D. V cross r hat is given. dA is capital R dx d phi. So dx d phi, capital R d phi gives me the arc length. If I multiply it by dx, basically I will find the area of an element here. So performing this integral over x and phi from 0 to 2 pi and minus w over 2 to plus w over 2, I obtained exactly the same result as in problem 28.76.